Today we're looking at electron configurations, which is section 3 of our chapter. As we look at electron configurations, what we're really looking at is how do we put electrons into the atom? Where are they now? We've looked at all the different things about the electrons in terms of where they can be, orbitals, sublevels, energy levels, but how do we put them in there? How do we know where they're going to be? And you might think this little cartoon ends up being what you're thinking about it, how boring it is coming from Niels Bohr. But really, it's pretty interesting on what's happening. So let's take a look and find out. So to start with, a quick review for us. Table we left off with the other day, just looking at our energy levels, which are N is our principal quantum number. 1, 2, 3, 4, it's how far away we are from the nucleus. Then our number of sublevels, how many sublevels each energy level has. And again, that's equal to your principal quantum number. It's equal to what energy level. And within those sublevels then, there are orbitals. So in energy level 1, we have one sublevel, which is the S sublevel, and there's only one orientation of that. We'll see those again on the next slide. So there's 2 electrons. The second energy level has 2 orbitals, which are the S and P, so there's one S. Then there are 3 different p orbitals, and each orbital can hold 2 electrons, as we see down at the bottom, 2 electrons per orbital. So when S has 2 electrons, 3 different p's, px, py, pz, have 6 electrons then. If you have a d orbital, which you start getting a d orbital in the third energy level, there are 5 of those, each hold 2, so you get 10. So 10 plus 6 plus 2 is 18, and 32 in the fourth energy level, and so on and so forth. So just quick review there. Now again, just taking a look at each orbitals, what they look like again. So an s orbital, you see as just the spherical shape, and there's only one orientation of that, so we have 2 electrons in it. The 3 p's, px, py, pz, each holds 2 electrons, total of 6 again in that p orbital. 5 d orbitals with 2 electrons each, so that's 10 electrons. The dxy, the dxz, the dyz, the dx squared minus y squared, and the dz squared, as we're looking at there. And then the f's, I put the pictures of the f's up here to see the 7 f's, but again, you don't have to be able to draw those or name those or remember those. You just need to know that there are 7 f's with 2 electrons each, so 14 total electrons. Now, continuing on then, to get to what we want to really look at is looking at how we put electrons in the atom. There are 3 basic rules we need to follow when we put electrons in. And the first rule is called the Aufbau principle, or the Aufbau process, it's also sometimes called. And really, that if you take that word Aufbau, kind of a weird sounding word, it's actually a German word. It's the German verb to build. So we're talking about the building principle in this case. And when we build things, whether you build a house or you're putting electrons into an atom, you always start with the lowest energy and work your way up. We don't build the roof first, we build the basement. Same with the electrons. We put them into the lowest energy positions first and then work our way up. So simply, we fill electrons into the lowest energy levels, the lowest energy levels, and those lowest energy orbitals in those energy levels, and then move our way upwards. So how exactly do we know what the lowest energy levels are and the lowest orbital energies are? It's not too complicated. We have this diagram here, which will seem complicated at the beginning, and what it's basically showing is it's showing us each orbital in its energy level. So the 1s, that's the first energy level, s orbital. 2s, second energy level, s orbital. 2p, second energy level, p orbital. They're just lining the orbitals up, but you can see that each orbital, as it goes up, this is our energy. So the higher it is on this scale, the more energy it's going to have. And so we always go with the lowest energy first. So you'd start in a 1s, go to the 2s, go to the 2p, then the 3s, the 3p. And then if you look very carefully, you don't go to the 3D next, which you probably expect, you go to the 4s, because that's just a little bit lower than the 3D, then the 4p, 5s, 4d, 5p, 6s, 5d, 4f, 6p, and so on and so forth. But you don't have to memorize this chart. I have a little different way for you to be able to figure out or find out what this filling order is going to be, what the lowest energy orbitals are. And so again, this is really showing us that the energy levels in their energy level order. The higher the energy is, the higher up the chart it is. Now this little star here, one thing that we're going to make a note of here and come back to later on, is note that the D and F orbitals actually have a higher energy, even though they're in a higher energy level than, or in a lower energy level than the next highest orbitals in an energy level. So the 4d doesn't fill until after the 5s. The fifth energy level is further from the nucleus, but the 4d has more energy, so it doesn't fill right away. Kind of strange, kind of could be confusing, but just remember that. Remember this order, or remember how to remember the order, and we'll do just fine. Now that filling order isn't too hard to do. If you can count to 7 and write numbers down 1, 2, 3, 4, 5, 6, 7, and write the orbitals 1s, 2s, 2p, 3s, 3p, 3d, and so on and so forth, you'll be able to find your energy level order. And that's what this little chart is here doing. Increasing energy, we're writing that going down in this case. We just write our energy levels in order 1, 2, 3, 5, 6, 7. All S's, then starting the second energy level, P's, starting at the third energy level, all D's, and the fourth starting with F's. And again, we're only talking about S, P, D's, and F's, so we don't have to worry about that too far. But what we're going to do to get that energy level order, this tells us that by if we take and we draw these arrows back down diagonally to the left, so start at the top right and move down to the left. If we start at this first arrow and we follow those arrows going down to the left, will be 1s. That's our first orbital. Now there's nothing else in this arrow, so we go to the next arrow and do the same thing, 2s. We just keep following these arrows, and those arrows are putting us directly into the exact order of energies for every orbital. So 1s, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, 7s, so on and so forth. And the reason that they're going in this order, this is the least amount of energy required to put electrons in. So remember this little diagram. That's going to be your key to knowing your filling orders. So again, that's telling us what the lowest energy levels and orbitals are, because we fill those first. That's the off-ball process. This next slide is also showing us the off-ball, a little bit more about the off-ball principle and the off-ball process. Again, it comes from the word off-ball and means to build. And electrons enter the lowest energy orbitals first. We list the orbitals from lowest to highest energy. That's what that chart did in the last page. And if we look at these numbers, you see this 1s2, 2s2, 2p6, and so on and so forth. Those numbers have a particular meaning. The first number is your energy level. What energy level you're at, how far from nucleus. This letter is your orbital. And then the number as a superscript is how many electrons are currently in that orbital for that atom. And we're going to see how the periodic table really helps us figure this out as we go along. There's some really good characteristics we've mentioned, but we're going to hit it a little bit harder a little bit later in this case. So you don't have to memorize the off-ball order. We can use the periodic table, which we'll learn a little bit later on, but we can also use that list we just saw on the last screen. Our second rule is called Hund's rule. As we look at Hund's rule is telling us something specifically not about all the orbitals and energy levels overall, but about each separate orbital itself, an s orbital, a p, a d, and an f orbital. And what it's saying is that before we can go and pair electrons up, because each orbital can hold 2 electrons, before it can hold 2 electrons into each separate orbital position, like if a p has 3 different orbitals in it, before I can put 2 electrons in the px, in the py, in the pz, I have to have 1 electron in each of those orbitals. I have to have 1 in the px, 1 in the y, 1 in the pz. Then I can go back and pair them up. And the reasoning for this is because if I put 2 electrons together in one orbital, the electrons are both negatively charged. And those negatively charged electrons want to repel each other. So if I spread them apart as far as possible by putting 1 in each separate orbital to begin with, then they're going to be as far apart as they possibly can be, which means we're going to have the least amount of repulsion forces, which means it doesn't take as much energy to put them in there. If I try to pair them up right away, and you'll see what I mean by that in just a second, then I increase the energy it takes to put them together, and it doesn't like to do that. Nature likes to take the easy way to do things like water runs downhill. It doesn't run uphill, it runs downhill. It runs to the gullies. It doesn't run over the high points. And the same thing happens with atoms still. Another way we can look at, though, we can think about Hund's rule, as well as I have this humorous diagram, which is called an approximation for it, which is called the urinal rule. And guys will understand this probably more than girls will right away. But in urinal rule, you think if you have a line of urinals, guys will go in and they will not stand usually right next to each other. They'll skip one in between until all the ones that are skipped are full. Then they'll go back and have to stand next to each other. And that's what the Hund's rule, the urinal rule, is kind of showing. It's showing us how Hund's rule is working. So here we have 6 urinals, which correspond to the 6 electrons in a p orbital, for example. And the first 3 guys come in, they're not going to all stand together in the first 3. They're going to get as far apart as they can be. That's what the electrons are doing as well. It's not till we have it half full that the next electron or the next person comes in and has to stand shoulder to shoulder with somebody else. A funny way to kind of think about Hund's rule and give us a real-life application of it as well. But that's what we're talking about. We have to half fill our orbital before we can fill or pair up electrons. Now the third rule is we're going to look at a couple different things here. But the third rule is called the Pauli exclusion principle. In this case, we talked about earlier in class that when we talked about quantum numbers, we said every atom has its own unique set of quantum numbers. Now for electrons in the same orbital, they're going to have almost all exactly the same set of quantum numbers, but one will be different. Because for electrons to be paired up in an orbital, they have to have this quantity that's called spin. In fact, they have to have opposite spins. Now the electrons aren't necessarily spinning, they're spinning somewhat, but it is determined by how they line up in a magnetic field. But electrons have to have this quantity of opposite spin to be paired together, and that's the Pauli exclusion principle. Now the way we show that is, here I have some diagrams, and this is what we call electron configuration notation. I have some elements listed here, and I have their orbitals that are present. Energy levels 1s, second energy level has an s and a p in it. Now what we do is we just go through the periodic table and say, okay, how many electrons does hydrogen have? Hydrogen has 1 electron. How do I know that? Again, because it's atomic number 1. So I show electrons with an arrow, and by convention's sake, we show up in arrows and down arrows to represent different spins. So hydrogen has 1 arrow, so it goes in the lowest energy orbital, which is the 1s orbital. And so there's 1 electron. I have all the electrons done. I go to helium. Helium has 2 electrons, atomic number 2. So the first electron is an up arrow, and the reason I'm only drawing half an arrowhead on these, because when you're doing lots of them, it's a lot faster to draw half an arrowhead than to draw a full arrowhead. But it has a second electron. Now Hund's rule says we have to have all the orbitals half full. Well, if there's only 1 orbital in the 1s, it's half full with 1 electron. So the second electron can pair up with it, but it has to have an opposite spin. So we're going to draw that arrow downwards. And by convention's sake, we always draw the first arrow up. It could be down, but just easier to do it up. Okay, lithium is atomic number 3. So first electron goes in the 1s. The second electron goes in the 1s. Now the 1s is full. So we go to the next energy level because now we have 1 more electron. So in the 2s, I put 1 electron. Okay, there's 1, 2, 3. Beryllium has 4. So you should get the idea here is 1, 2, 3, 4. Boron has 5. Notice I'm going in order of atomic numbers. 3, 4. The next electron goes to the next highest energy orbital, which is the p orbital. Now here's really where Hund's rule is going to come into play. In carbon, 1, 2, 3, 4, 5, 6. Notice these electrons are not paired up with each other. It's all a p orbital, but they have to be as far apart as possible and go separate orbital positions. Okay? Then in nitrogen, the same thing is true. 1, 2, 3, 4, paired up, 5, 6, 7. Because nitrogen has 7 electrons. Now, if you look at this orbital, that p orbital holds 6 electrons. So by having 3, it's already half full. So if I want 1 more element to oxygen, 1, 2, 3, 4, and then the 2p would have 5, 6, 7. Now we go back and put in that 8th electron to pair it up. And then fluorine would have 9 would be paired up, and neon would have 10 to be paired up. Okay, so these are electron configurations. The line is representing how many orbitals there are for each one. So a p has 3 different orbitals, px, py, pz. That's what these lines represent, the px, the py, and the pz. If I have a d orbital I'm going to be showing, there'll be 5 lines. If there's an f orbital, it would be 7 lines, and s has 1. So that's our application of all 3 of our rules, the Aufbau process, the Hund's rule, and the Pauli exclusion principle. Now, that's what we call, again, electron configuration notation. We have another way we represent electron configurations, and that's what we call orbital notation. Orbital notation is a little easier. It's a little shorter. You don't have to draw all the lines that are involved. Instead, in this case, we're just showing which energy levels, which is the number, the orbital SPDF, and how many electrons are in that orbital, like as a subscript, or a superscript, I should say. So here's the differences. Oxygen was O, 1s2, 2s2, so it's up and down, and then there's 4 electrons in a P, so 1, 2, 3, come back and 4. We draw the electrons with arrows. In orbital notation, I just use numbers to represent how many electrons there are in that orbital. How many arrows are in the 1s? 2. How many arrows are in the 2s? 2. In the 2p, all 3 of those lines, there are 2, 3, 4 electrons. And there you have orbital notation. Now, the periodic table, we come back to that a little bit because that gets to be really important as we look and see there. Some of those things we talked about as being coincidences. There really aren't any coincidences on this table. When I take this table, if I can take it and I draw some lines here, divide this up into some blocks, those blocks are going to be important to us. Because this first block, how wide is this first block? It's 2 elements wide. 2 elements. Does anything else have 2 in it? An s orbital does. So this is what we call the s block, because in this part of the periodic table, the electrons are going into the s orbital. Way over here on the right, this block is 1, 2, 3, 4, 5, 6 elements long. 6 elements, 6 electrons. A p orbital has 6 electrons. So this is what we call the p block. The transition metals here are 10 elements wide. That's a d block, because a d orbital has 10 electrons. And the rare earth metals at the bottom are 14 elements wide. That's the f block, because again, the orbital that you're in, the block you're in, is telling you which orbital your electrons are in that case. So it's not a coincidence that those elements, or those rows, or those blocks are that many elements wide. And just as we saw, if we looked a little earlier too, we saw an S had 2 electrons. First row has 2 elements in it. The second energy level had 8 electrons that could be in it, 2 from an S, 6 from a P, and it was 8 elements across. Okay, that's not a coincidence. Periodic table is a marvelous thing. So, and we're going to hit that a little bit more towards the end of this presentation. But again, the block an element is the orbital that's filling. So if I pick an element like antimony right here, if I picked antimony, antimony is in the p block. That means it's the p orbital that's getting the electrons in it. Every orbital before it will be full, but that will be my one that's filling. That will be my very last one that I'm going to worry about with my elements. So if I go back to that table earlier, the filling order, I would go, where is that p block at? And we'll tell you about how we can figure out which p it is here shortly. And I can say, that's my last orbital. That's the last. Everything else I'm going to have up to that one, and there, fill everything but that orbital, and just know how many electrons are in it. So again, if we take a look here, a couple things that we notice is that if we look at our rows, 1, 2, 3, 4, 5, 6, this is 1s, 2s, 3s, 4s, 5s, 6s, 7s. The rows are actually equal to your energy level. What row an element is how many elements, how many energy levels that it has. Okay. Now, if you look real carefully here, notice that the D and Fs are filling later. We said, okay, the second energy level had 8 electrons in it, had 8 atoms. We said the third energy level should have 18, but you count the third row, there's only 8 here. Where are the missing 10? Well, back in the off-ball principle, you saw that the Ds didn't fill before the S of the next level. So the Ds are actually filling one level later. So while this would be the 4S, this would actually be the 3D. And if you go back and look at the diagram again of the energy levels, orbitals in the energy levels, and the filling diagram, you would see that the 3D was a little bit higher than a 4S. So we come back to it in each case. In the Fs, we come back 2 levels later. So we would have an F in the 4th energy level, but you notice this is S, D, and P. We have to go all the way down and fill the 5 before we come back to it, and then 6S before we come back to the 4F. And we'll look at a little bit later how you can figure out exactly what's going to be happening in that case, because actually this element fits in right here. And this element fits in right here. So this would be 6S. We start the 5D, go to 4F, finish the 5D, 6P, 7S, 5F, 6D, 7P. Okay, that's going to be your order. If you do the little chart with the 1S, 2S, 2P with the arrows on it, you'll see that's the exact same order it's coming. The periodic table is set up in the order of filling of the elements. Pretty amazing, isn't it? Now the periodic table, one thing we can look at the periodic table in this case is that also in the position that an element has in the block, that's how many electrons are in that orbital. So in this example here I have zinc. Zinc is in the D block. And so this would be the 3D because the first D level is the third energy level. So 3D. And it's 1, 2, 3, 4, 5, 7, 8, 9, 10th element in it. That means it has 10 electrons in that block. Okay, so the D orbital will be the 3D would be the last orbital in my filling order, and it has 10 electrons in it. So that means I could really quickly go through, and I know my filling order, to put all the electrons in, say I know I'm going to end at 3D10. I don't even have to count the electrons at the end to know that I'm going to have the right number of them in it. But anyways, it'll be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Again, that comes from right here. 1s2, hydrogen, helium, 2s2, lithium, beryllium, 2p6, these elements, 3s2, because it's S block again, 3p6 from the P block, 4s2, 3d10, that element. And if it was a different element like cobalt, it would be 3d7. If it was titanium, it'd be 3d2, because it's at the element that you're in. So all you have to do is count how far in the block your element is, and that's how many electrons are in that orbital. So how many electrons would be in the last level of phosphorus, which would be the 2p, 3p? If you said 1, 2, 3, 3p3, you were correct. Now, writing out long elements isn't going to be a lot of fun because if we have 118 electrons, that's a lot of electrons to draw, or a lot of orbitals to write. So we also show a shorthand orbital notation. And the shorthand orbital notation is only showing us the last row of the electrons that are being filled in. All the other electrons that are below that, or rows above it, are going to be exactly the same as whatever noble gas is at the end of that previous row. So we're going to show the noble gas and then show what those last row configurations are. So here we have an example again. So we're taking zinc. What we see is here's zinc's actual configuration: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Okay. Now, if I go to the row above zinc, argon is a noble gas in that row. And argon's configuration is 1s2, 2s2, 2p6, 3s2, 3p6. That much of it is what argon would be. So zinc is really argon plus some more electrons in it. So what we're going to do is we're just going to take and show these first whole bunch of electrons that have argon's configuration as AR in brackets. And then we just show what's left. These are the electrons that are filling from this last row, 4s2, 3d10. So this makes our configurations a lot shorter, especially as we get down to bigger and bigger and bigger atoms. We can take whatever the noble gas is of the row below it, or a row above it, then write down what's left. So if krypton was my atom, I'd be krypton's configuration, 6s2, 5d1, actually 4f14, 5d10, 6p6, whatever order or combination of elements I have to figure out where I am in that case. Okay, we'll talk about those a lot more in class and write a lot of those, so we'll get to better at them than what we're going to show in this short presentation. But you can look at that a couple times and look at that explanation, and that should really help figure out what's going on.